Like he said, I'm Gingerich. I'm a first-year PhD student studying under Dr. Wayne Strasser. My research focuses on using direct numerical simulation to study flow over shark skin. This presentation is going to be talking about the problem is flow separation. Our solution could be shark skin, and our goal is for shark skin to provide passive boundary layer control. So let's look at our motivation for this topic. Passive boundary layer control applications, both hydrodynamic and aerodynamic. Got airplanes, racing cars, ships, submarines. Let's take a closer look at how they could be used on aircraft. Got a regular airfoil. As it increases its angle of attack, you got flow separation. Let me get my laser pointer out. You got flow separation right up here at the top of the airfoil. Let's zoom in on that. So we got velocity profiles in orange, white are streamlines, and in this area of flow reversal is where we see the boundary layer separation. Right as the flow is starting to reverse, that's the boundary layer separation point. So if we want to passively control this boundary layer, if we want to keep the boundary layer attached, then we need to inhibit this flow reversal. This boundary layer separation is bad for airfoils, obviously. When it separates, it's called stalled, right? And the lift coefficient drops dramatically. So some of the effects: increased pressure drag, higher energy consumption, and reduced maneuverability. That's not just for aircraft, that's for ships, cars, etc. So how can sharks help? Well, sharks have these tiny little scales called denticles. They're on the scale of about 100 microns. Here's a scanning electron microscope image of one. These are riblets on top, and they help to reduce turbulent skin friction. But there have already been many papers on how these riblets help reduce turbulent skin friction. I'm going to be looking at how these shark skins, these denticles, can actually bristle up into the flow to help prevent separation. The picture on the right has been manually bristled in a lab. This angle turns out to be pretty important. Right along the flank of the shark here, that's where you see the scales with the largest bristling angles. If you view it from the top, that is right after the area of maximum thickness, and you have a lot of high curvature from the swimming motions. So these two areas are where we would expect to see a lot of flow separation, and they would require the most control. So it's interesting that coincides with the denticles that have the highest bristling angles. So some work done by Duclos, they actually managed to observe this bristling action. There's a vortex occurring upstream of the denticle, and then on the next time step, you see the denticle bristle up into the flow and stop that vortex, and inhibiting flow separation. Some more work done by Santos. The color map is the fraction of time the flow is reversed. So right at 50% is where we would see flow separation. This is a Reynolds number of 4.9 to 5. On the left, that image it's over a flat plate. The middle image is shark skin with a bristling angle of 30 degrees, and on the far right is bristling angle with an angle of 50 degrees. As you can see, 50 degrees, it eliminates flow separation entirely, but bristling angle of 30 degrees, if anything, it increases it. So this bristling angle is very important, and this supports the argument that bristling up actually inhibits flow separation. They did the same thing with a higher Reynolds number, 7.1 to 5, and 8.1 to 5. So that's a little bit of the motivation for my work. Let's look at some of the methods that we're going to do. So the previous work has examined the large-scale characteristics of the flow. It is lacking the fine-grained detail that direct numerical simulation can provide. DNS is useful at very small scales, such as the denticle, and it resolves all the turbulent flow scales. It can visualize the flow in the boundary layer, and it will give us much broader quantity of data than the experimental. It's also very computationally expensive, however. So it requires a lot of validation. So first of all, to get this DNS study of turbulent flow over bristling shark denticles, we're going to need to validate our DNS methods we're going to need to have a 3D moving and deforming mesh. Then we're going to need to add two-way coupled fluid structure interaction. And then finally model and mesh the real denticle geometry. So right now, for this presentation, we're just focusing on the 3D moving and deforming mesh for just a proof of concept denticle, very simplified geometry. So in a dynamic mesh, the mesh is adjusted to capture the movement and deformation of the cell zone boundaries. So we got a denticle in there moving up and down, and the mesh needs to deform to capture that movement. So there are three methods in ANSYS Fluent, which is the software we're going to be using: smoothing, remeshing, and dynamic layering. Here's an example of 2D smoothing and remeshing. You see smoothing acting in here to absorb the motion of the boundary. The interior nodes absorb it, but there's no change in the nodes or the connectivity. But it cannot absorb large boundary displacements like we would see with the denticle. This is why they use it in combination with remeshing to agglomerate the badly skewed or sized cells. You see this happening closer to, like, right at the tip of this moving door. It remeshes those agglomerated cells, but this is only available for tetrahedral elements, which are more diffusive than quads. So now let's compare that to dynamic layering. Dynamic layering adds or removes cell layers next to the moving boundary, but this is only available for prismatic elements. So here's an example of how this could be implemented. This is just 2D, obviously. But this is only, So this region right here is just rigid motion prescribed by a UDF. These two areas are the dynamic mesh zones that utilize dynamic layering. And this area right here is a sliding mesh interface. These two are the moving boundaries. So now let's look at that movement again. So let's compare dynamic layering with smoothing and remeshing. Hexahedral elements with dynamic layering, tetrahedral elements with smoothing and remeshing. Obviously, I said before, more diffusive. Dynamic layering is less computationally expensive to constant, so it's not constantly having to remesh it like in smoothing and remeshing, especially in 3D remeshing can get really slow. Dynamic layering, however, utilizes sliding interfaces, which can produce kind of numerical garbage right there at the interface. Smoothing and remeshing does not. But dynamic layering maintains this high quality mesh right near the denticle itself, whereas smoothing and remeshing is constantly having to remesh these cells right next to it, so they can oftentimes get skewed. So now let's go put this into 3D. This is the model that we've been running. Got an inlet here, symmetry planes, a top wall, outlet. This is the denticle moving in the center. 3 millimeter size, inlet velocity of 0.5. We're seeing a Reynolds number of like 120, definitely in the lambda range. So the interior mesh surrounding the denticle itself is moving with the denticle, but the exterior mesh is stationary. So right here, there is the sliding mesh interface, and that has the potential to mess up our drag calculations. So here's just another view of that. You can see the yellow small cells on the interior sliding past those red cells on the exterior. So those are some of our methods. What are we seeing from our results? So these are different contour planes where I'm showing velocity contours. This is just the velocity magnitude normalized by the inlet velocity. So you can see, like, right along here we have the sliding interface going on. You can see a little bit of distortion in the velocity field. So how much is that going to affect our drag? Is that a fine? Well, we remeshed the domain without sliding interfaces, and obviously without sliding interfaces it can't move. So we did it at steady state in the original starting position, and we saw an error of 0.013%. So very little impact on the drag force at the denticle itself. If we look at so U2 is the velocity field of the mesh without sliding interfaces, and U1 is the one with sliding interfaces. So the difference is right at the mesh interfaces themselves. We see a maximum of 5% difference acting right behind the denticle itself. But as you can see, right near the denticle, there is 0% difference between this and the one without sliding interfaces. So as long as we can keep those sliding interfaces far from the surface we care about, we are fine to use this method in future studies where we actually mesh the real denticle geometry and implement FSI. We also tried different solution methods, seeing if that would have an effect over the sliding mesh interfaces, and nothing made any higher of a difference other than 0.4% drag difference, which was 3 times this time step, the normalized time step. So those are my results. In the future, like I said, we're hoping to implement FSI and real denticle geometry, but that is all I have for today. Thank you.